Hello everyone. In this video we will see some examples of matrices with real entries but complex eigenvalues. This may come as a surprise, but let me just tell you a few things that shows that this should be a very natural thing. Well, I remember that while working with real numbers, when we work with only real numbers, complex numbers appear as roots of equations, as roots of equations. So we may have just real nice equation, and then when we try to solve, the complex numbers come up like, and this is almost the one thing that will happen. But why this can happen for eigenvalues is, recall that eigenvalues are roots of the characteristic polynomial for the matrices. So we're basically trying to solve an equation, and well, though all the entries are real and characteristic polynomial, all the coefficients are really real, but the eigenvalues can be complex. Let's see this in example. So characteristic polynomial of this matrix A lambda, so this is determinant of A minus lambda I, but this is the same thing as 4, 3, negative 1, 2 minus lambda, and then you find that 4 minus lambda minus 3 times negative 1, and that is what? That is lambda squared minus 6 lambda plus 8 plus 3, so that is. Now eigenvalues are when we set this guy is equal to 0, and well, since this is quadratic, we can use the quadratic formula. So minus b plus minus b squared minus 4ac divided by 2a. So this is 6. Oh, actually I can separate these. What I get under the square root is 36 minus 44, which is minus 8 divided by 2. Minus 8 is not a real number, so but you can write it as root negative 1 times root 8, which is the same thing as writing root negative 1 to root 2. And then you cancel that 2, so you get 3 plus minus. This guy is I root 2. So 2 eigenvalues. These are the eigenvalues. The entries were real, but the eigenvalue was complex. How do we go with the eigen vector? So we do exactly the same way as we did for numbers. So basically, let me just fix one of these guys. We try to solve a minus lambda I times xy equals to 0, 0. So in this case, that will give me, look, this is a minus lambda I, but I plug in lambda 3 plus root I root 2. So that will give me 1 minus I root 2 times x plus 3y equals to 0. The other one is minus x plus Yeah, okay. So 2 minus lambda. So this is 2 minus 3. This will give me minus 1 minus I root 2y. Remember from the other examples that we had for the eigenvectors, these two guys must be multiple of each other. So are multiple of each other. But this is a nice algebra thing that you can do here. How do you see that? Well, if I multiply the first row by negative 1 minus I root 2, let me multiply it. Sorry, minus 1 minus I root 2, that will be 1 minus I root 2 times x. This is just showing you that this is multiple of the other one. So here now I have two complex number I want to multiply. So that will give me minus 1 times 1 is negative 1. Minus 1 times minus I root t, so this will plus I root t. Then this guy here, this is minus I root 2. And then this guy here is, you see, minus 1, negative, negative, they will cancel out. I times I is minus 1. Root 2 times root 2 is 2. This is x. Oh, there was a y here. I dropped it. So this is 3 times minus I, minus 1 minus I root 2 y equals to 0. And you see this cancels with that. That's negative 3. And you see that negative 3 of x, or sorry, just 3 minus x plus negative 1 minus I root 2 y equals to 0. This is basically 3 times equation 2. I started multiplying this by equation 1 and I got the other one. So these are multiple of each other. It's always going to be true. One will be multiple of each other if you have done everything correctly. So that means that I can go ahead and use one of these guys and find the relation between the components of eigenvectors. So this will be y is equal to 1 minus I root 2 divided by 3 of x. So eigenvectors are going to be 1 minus I root 2. Okay, sorry. First one is x. The second one is 1 minus I root 2 divided by 3x. In particular, if x is, let's put it 3, this one will be 3, 1 minus I root 2 as an eigenvector. You can similarly find an idea, another case there. So for example, for eigen, similarly, eigenvector for lambda equal to 3 minus I root 2. Did I make a mistake? Yes, I did make a mistake. This should be negative because I'm taking that to the other side. So this must be plus and that must be like that. Yeah. You can do similar kind of work there and you will be able to get something like I don't know, negative 1 plus root 2I times 1 here, something like that. So that's eigenvector for that, but similar work needs to be done and you can complete that one. Let's do another one here. So characteristic polynomial, determinant of 1a minus lambda, only on the main diagonal. So we do then 1 minus lambda squared minus negative 1 times 1, which is lambda squared minus 2 lambda plus 1 and plus 1. That is lambda squared minus 2 lambda plus 2. Then lambda is eigenvalues. Solve that one. 2 plus minus root negative 2 squared 4 minus 4ac divided by 2. That's 2 plus minus root negative 4, and that would give me 1 plus minus root negative 1, which is I. So for 1 plus I, we do get 1 minus I plus I, negative 1, 1, 1 minus 1 plus I times xy equals to 0, 0. From there, you see that minus I, x minus y must be equal to 0, and x minus I, y is equal to 0. Again, these are multiple of each other. Well, actually, if you do multiply equation 1 by I, you get equation 2. So the only thing I need here, so let me just write this one in red so that you don't confuse it with the other things. So solving that one, this will give me, so minus ix minus y is equal to 0. That means that second component is going to be negative ix. So that means that eigenvector are going to be x minus ix. In particular, if x is 1, you may get 1 minus I. Also, this is interesting that you now can plug in complex numbers. For example, you can plug in or you can plug in I there. If you plug in I, the first one is going to be I itself. The second one, I times negative I, is 1. These are multiple of each other. It's just one is I times the other one. Those are how you can find those eigenvalues. For eigenvectors, for 1 minus I, on the other hand, you get 1 minus I minus 1 xy equals to 0, 0. 1 minus I. So from there, you get ix minus y equals to 0. From here, you get x plus iy is equal to 0. These are the same things, just one is multiple of other one. So I pick one of these guys, and I see that here now the second component is I times the first component. So eigenvector is going to be x ix. In particular, if you set x to be 1, this is 1I, or, well, anything you can put there, or any complex number, if x is equal to, say, I, then you will get I negative 1 here. So there are infinitely many eigenvectors there for each one of eigenvalues, but the point is that every single one of them is multiple of the other one, and that's how you find those ones. Okay.